news articles. This one I see getting a lot of attention. There is a guy making a TikTok claiming that he was thrown out of his college for finding some kind of security vulnerability and reporting it, but it's fake. And this is apparently a new thing on TikTok, is you pretend to be a hacker and post fake hacks. He's got a teacher's account to Canvas, and he opens it and pretends to be a student and such. So see, someone says they have audio problems. Other people said they heard me a minute ago. Do other people hear me? Let's see if there's any more put in chat here. Right up there, a couple of people said they heard me. You're hearing me. Okay, good. So Globnet, maybe something wrong with your machine. Good. Okay, thank you. Anyway, I saw a whole bunch of people falling for this. So this is a big issue. A lot of hacks you see are fake, of course. So always be careful. A lot of people make fake hacks for various reasons. A student pointed this out earlier today. Looks like a good talk on Tuesday coming up. A SANS webcast on jailbreaking iOS. So it sounds pretty good. I've got a homework for jailbreaking, and several students borrowed phones from me to jailbreak, and they're having trouble using my old instructions from a year or two ago, so I'm going to have more instructions with more up-to-date ones. I'll probably get those ready by next week, but it might be good to attend this and learn more about it. City College is having ridiculous cuts. They announced this. They've gone really bad. I know 4 full-timers in our department got these pink slips. I didn't get one because I think I had more seniority, but the way it works, they send you this scary legal letter that looks really terrible, like you're absolutely fired. And I think it's not true, but nobody really knows. I think they have to pretend to fire a bunch of full-timers so the department will be pressured into really firing the part-timers. But it is pretty awful. Cydia tweaks. Let's see, somebody's posted a link here. List of iOS, all the coming features on jailbreak. Oh, neat. Okay. That looks like a good one. Uncovers latest jailbreak. Yeah, that's a good one. Let me throw that in the news links and on Twitter. That's a good thing to have. And I may be using one of them to write up instructions because, I was using the check rain exploit, but from what I'm hearing, it's no longer the best one. And so we should switch to one of these newer ones. Anyway, everyone's getting very upset. There's ridiculous amounts of cuts. City College is smaller than 1/4 of its original size from just 8 years ago. So it is really ridiculous. And especially since it's done by seniority, it's going to be all the younger teachers getting fired. Can you jailbreak without a shim? Yes, I think you can. I think I've done it before. But I'll let you know. This is something I've heard about, but I haven't seen yet. They're supposedly going to have a COVID-19 passport required to enter places. I wonder if this can be legal in America. That's all that concerns me. I know they're doing it in India, and I think China, there's an app. Anyway, we'll see what happens. I know there's a lot of people that have these thermometer guns they point at you, which is just security theater from what I can tell. I don't think your temperature tells them much of anything useful at all. But anyway, we will see if we get this kind of stuff. I know this is all over China. Yes, fake documents would be easy. There was, I think, an Indian app where, yeah, that's good. Lando says the same thing I thought, that you don't need a SIM for a jailbreak. I think you might need a SIM to actually connect directly to the telephone network. But the jailbreak, you can still use your computer for internet services. Now, somebody told me you can actually make normal phone calls with just a Wi-Fi connection. And so I'm sort of interested in figuring out how to do that if that's possible. But anyway, we'll see what comes of this. I saw a while ago there was either Indian or Chinese, I think it was an Indian app that had like a green sign saying you're not infected, and it was very easy to hack to just show the green regardless of the actual signal. So I would imagine I know there is a market in fake vaccine passports. You can buy them for like $100 or $200 to get on airplanes. I've read about that. So like any other credential, there will be fakes of it floating around. So here's hafnium, a threat group. You can tell Microsoft named them all after metals, which, by the way, is a terrible idea, because if you try to Google magnesium or something, you'll get all these metallurgy and chemical hits instead of being able to find the group. I wish they would all just settle on one system like APT35 or something. No, I'm not on mute. Other people can hear me, Levon. You should be able to hear me through Twitch, but not through whatever this other thing is, Zoom. No, people seem to be able to hear me. Sound is on Twitch, but not on Zoom. Don't use Zoom for sound. Hopefully people will figure it out. Anyway, so there's supposedly a big 0-day being exploited in Exchange. Bottom left on Twitch is the volume button. And like everybody tells me, I don't see one of those either. I can never find the button to show the chat, and I don't see the volume button, so it seems like other people see different things on Twitch than I do. It's, as far as the, there is nothing on the bottom, on the left of my Twitch except a yellow live Sam Bound. There's no obvious volume button. But anyway, I'm okay, but apparently there are different ways Twitch looks, because I often get told instructions how to do things on Twitch, and none of them seem to really be true for what I see on my screen. Anyway, so Exchange Server has this vulnerability, and everyone's saying you need to patch right away. Right above the yellow live, when you hover, there's nothing above the yellow live at all. Oh, up there. Oh, you're right. I found it. That's interesting. Okay, thank you. Neat. Okay. If I unmute on Zoom, then everybody will hear everything twice. It's why I cannot use Zoom and Twitch at the same time without muting one of them, or you'll hear like echoes and delays and everything. Yep. All right, well, we'll see. Hopefully you folks can work it out. Maybe you can tell people how to operate the Twitch, because I'm no good at operating Twitch. There's a keyboard, an M keyboard. I don't know what that is. Okay, keyboard M to mute it. Anyway, yeah, I don't know why my Twitch is not sending out any sound, but I don't really care. Anyway, let me know if you continue to have trouble, or post a comment about it. And anyway, hopefully the other students can tell you how to get the sound into Twitch. Anyway, I think that's probably enough news. I think it is. We can carry on to the official stuff here. All right. So we're CNIT 125, and what we're going to do today is the last bit of security engineering, which is primarily cryptography, and a little bit of physical security. And there may be some people that want to do presentations. I have one so far. If anyone else wants to do a presentation, let me know. But I'll do those after the lecture. Yeah, seems to toggle mute, but it does not work all the time. Yeah, all right. So let's get on to here. And I got to go up. A, B, C, D, E, F. Okay, the start of this section is where we are. Okay, A, B, C, D, E, F. Okay, this is where we left off. Okay. Okay, so glorious cryptography. The M on your keyboard worked. Good, I'm glad you folks got it worked out. Okay, so in Sparta, they would take a stick like this and write out the message this way, and then unwrap this so it would scramble the order of the letters, but not the letters. Like I said, this in the ancient times, more than 2,000 years ago, very few people could read writing at all. So any little trick that scrambled the letters even a little bit was considered military-grade encryption. So the Caesar cipher was just move all the letters forward a couple of steps in the alphabet. Another simple trick that again was considered good enough. ROT13 is actually used by Windows to so-called protect your privacy with your Internet Explorer bookmarks in the registry. But it's, of course, a terrible system, far too weak to really hide anything these days. A much stronger system is this Vigneri square, which I imagine I'm pronouncing wrong. I think his name is French. But the point here is you can have a keyword like flower, and then you would use the F dictionary for the first letter and the L dictionary for the second letter and the O dictionary for the third letter and so on. So you use a different dictionary for each letter, and that makes it much harder to break. It's like a mixture of several of these shifts with different shifts. And there are these things where you rotate the wheels. So by rotating the wheel, you can easily shift forward if a letter in the alphabet or so on, or even have a backwards one. So, there's a lot of these techniques. I think they use this one in the, something like this in the Confederate Army. These simple screens. Here's something I think for the Confederate cipher disk. So, these are all simple substitution ciphers, and they scramble text so that it makes secret writing. Then there's the book cipher, where if you have a book, exactly the same book from the sender and receiver, you can just pick words out of the book and just put like page, paragraph, and word number. And then the only way to crack it is to have exactly the same book. So, then you got running key cipher, like I was talking about here. Attack at dawn, and then you use like a constitution here, we the people. So you have this long text string, and you shift it by all these amounts, and so it amounts to a lot like the book cipher. You have to find this key phrase. You'll never be able to decipher it without finding that key phrase. There's no mathematical analysis that will do it. And then there's codebooks. Codebooks were actually used in telegraphs early on just to save money on telegraph transmissions. They would use short numerical codes for long repeated phrases. The Secret Service uses code names for people. But the perfect encryption scheme, which has never been broken and probably will never be broken, is the one-time pad. You have the sender and receiver has to have a pad with pages full of random letters, and you only use each page once, and you never reuse it. So you scramble each letter based on the letter matching the pad. You cross them out as you go, and there is no mathematical pattern at all in the output. So there's no possible way to break it without getting a copy of that pad. So this was considered very good. Vernam used it in 1917, and it was very effective. The only problem with it is there's a huge key distribution problem. You must somehow distribute this entire pad of one-time pad to the other person without anybody being able to get an extra copy of it. And you can only transmit as much message as you have pad, and then you have to somehow get a new pad there. So if you can overcome that key distribution problem, you've got an essentially perfect system. But the distribution makes trouble. The KGB used it in the 1940s, and the problem is they cheated and reused the pads more than once. And if you do that, then the security goes way down. Anyway, then there's these Hebron machines, an Enigma used by the Nazis. These are things that look like typewriters, but they have extra gears in there. So when you type the key, a different letter is printed on the page. And anyway, these are all fine, but they're, of course, they broke them by actually getting copies, finding machines with this. So anyway, this is the science of secret writing. Is primarily advanced by the military, and then weaker versions of it are used by civilians for banking and such. So we've had a lot of laws to control export to Iron Curtain countries to try to stop them from having strong cryptography. And we finally had the Wassenaar arrangement in 1996 when the United States finally stopped worrying so much about exporting cryptography, but it is still restricted. And when I tried to teach my cryptography class in China, I was warned that I'm not allowed to do that by U.S. law, even now. So I didn't. Anyway, so symmetric encryption is the ancient kind we've already had, where there is a secret key and both the sender and the receiver have to have a copy of the same key. That's the standard kind. That's the only kind of encryption that ever existed until asymmetric encryption was invented in the 1970s, which is amazing, where you do not need to transmit the secret key. Instead, each user has to have two keys, and we'll talk quite a bit more about that later. There's also a cryptographic process called hashing, but it does not provide, it's not used to send messages. It's used to check files for integrity, and it does not provide confidentiality. All right, something is beeping, some kind of message coming in, but can't figure it out right now. Anyway, so that's symmetric encryption. This is also secret key. You have a serious problem here. It's kind of an oxymoron. You have this thing called a shared secret. You have this secret key, and you somehow have to give it to another person, and the two of you have to not lose it to a third person, but there's no way either of you can be sure that that has not happened. So that is the fundamental weakness of this. How can something's hash be easily looked up on the internet? You can just Google them if they're using simple systems like Microsoft hashing. That's the problem. But if you just Google them, you'll often find hashes have already been cracked for you. That works for Microsoft passwords. Anyway, so stream ciphers encrypt your message as the host of the exe file shows the hash on that page. Yes, some people put hashes on a page. That can happen. That's not considered a very secure system because someone could hack your server and change the number on the page. A proper digital signature is better, where you have a cryptographic signature signed by a real certificate authority on the file, but that costs some money. All right, so if stream cipher, you break your message into a stream of bits, and then you just encrypt the bits one at a time. This is used by WEP and RC4. The more common system is the block cipher, where you have blocks of data, like 64 or 128 bits, and you encrypt one block, and then the next block, and the next block. They both amount to the same thing, and they can both be quite secure if you use a good modern system. The initialization vector is a random value added to the plain text before encryption and then transmitted along with the ciphertext. It's not a secret, but it has the result of making sure that if you have two identical plain text messages, they do not have identical ciphertext. That way people can't notice if you're still sending the same request twice. Then there's cipher block chaining is a technique where you take the output of one block to use as a seed for the next block, and it makes the resultant ciphertext more random to conceal patterns in the plain text. DES was the first approved American standard for encryption, and this described the Data Encryption Algorithm. They had a contest where companies could propose cryptographic routines to see which one the U.S. government would approve. IBM proposed a 128-bit system, which would have been very strong. The DES, under pressure from the NSA, secretly, the NIST lowered it to a 56-bit key so that the NSA could crack it, and they told everybody in America to use dangerously weak encryption. It was a big scandal, and part of what continues to this day. There is a huge pressure. The National Security Agency wants to enforce something they call no-bus. They want to make a system with a secret backdoor that the NSA can get in, but nobody else can get in, nobody but us. That's their goal, and it turns out that repeatedly has led to them either explicitly advocating unsafe systems or even lying and bribing people to use unsafe systems, and this was the first of many examples of that happening. DES is no longer considered safe for any purpose because that 56-bit key is too short. But DES did define these modes, which continue even for the modern AES. Electronic codebook and cipher block chaining are the most common mode, but these counter modes are actually the more secure ones. So electronic codebook is what they call textbook encryption. You just take blocks of plain text and encrypt them, and then you take the next block and encrypt it, and the next block and encrypt it without anything else happening. The problem is if you have two blocks of identical plain text, you get identical ciphertext. So that means if you encrypt an image like this, you'll get a block of solid color like white. It will just turn into the same block every time you encrypt it, so you can still see patterns in the output. That's what happens with electronic codebook mode. Identical block of input turns into an identical block of output. Cipher block chaining. Well, the NSA doesn't actually enforce any of these, but what they do is they define a government standard, and then anybody who wants to do business with the government will use the standard. So they didn't force people to use it. But they're still quite influential, of course, because software and hardware manufacturers will generally manufacture stuff to meet the government standard, and banks and everybody will just do the standard because, because of their market power. In America, they don't force you to do it with a law saying it's illegal to use some other encryption, but once the government has a standard, everybody pretty much wants to use that in order to do business with the government. So CBC mode, each block is encrypted, and then you use that output, the encrypted output, as something to add to the next block to make it different. So now it encrypts into this, which is what you expect by encryption. All the patterns are gone, it's just random snow. And all these other modes have the same effect of not having any repeated patterns here, so they look a lot better. There are more subtle weaknesses in some of them, but they're all a whole lot better than electronic codebook. So single DES was the original one single 56-bit key. The problem is 56 bits means there are only 2 to the 56 possible keys, which is not a big enough number. 2 to the 10 is 1,000. 2 to the 50, it's 10 to the 15. It sounds pretty big, but they were in fact able to try all those keys in 1997, and it's even faster nowadays. So nothing is safe with only 56 bits of key. You need more key lengths. So the next step up was triple DES, where you do 3 rounds of DES using 2 or 3 different 56-bit keys. So now the effective key length is 112 bits. And that is considered quite secure. 100 bits of key is enough. Nobody can do 2 to the 100 calculations ever. I watched someone demonstrate a padding oracle attack. Oh yes, it is pretty easy to crack, and we do it in the cryptography class. Yes, that's the weakness with CBC. But it's not intrinsic to CBC. It happens if you have a defective implementation that gives you an informative error message that tells you when the padding fails. So it's a combination of CBC and a information leak from an overly informative error message that makes it easy to crack. Properly implemented, CBC can be fine, but the most secure mode is now the one called Galois counter mode, which again I think is some French word I can't pronounce. When you say crack, do you mean using Hashcat or John? For crack a hash, you can do those with Hashcat or John, yes. That's one way to do it. There are other tools and other ways, but yeah, that's cracking a hash. Yeah, all right. So anyway, this triple DES is perfectly fine. It's just slower, and you might as well use AES, which is the modern equivalent. But if you have some hardware or software running triple DES, that's considered quite strong. All right, now there are, when they did the competition to define what would be AES, there were runners-up, which were algorithms that were proposed, that were examined for a few years, and they seemed perfectly fine, but they just weren't the one chosen to get the government stamp of approval. So there are several well-known algorithms that people can use, but they're just not the official one approved by the government. And IDEA is one of them. It has a 128-bit key, 64-bit block size, but it's encumbered by patents, so you'd have to pay to use it. AES is the one the U.S. government made to replace DES, and it is considered very good. It has a 128-bit key or 256. In principle, there's 192, but I've never heard of anybody using it. And it's patent-free. It goes very fast on modern computers. And this is generally what you use for a secret key cipher. It's by far the best thing to use. It's very hard to understand why you would use anything else unless you really, really, really hate the government. And you're just convinced on a conspiracy theory, sort of thinking that anything the government approves must be bad. And then you would use one of the other runners-up like IDEA or something. So here's the 5 AES finalists: Mars, RC6, Rindjael, which is AES, Serpent, and Twofish. And they're all perfectly fine. They're all perfectly strong in principle, but the one that's officially approved by the government is Rindjael, which is AES, so that's the standard in America. And it just has a series of steps. You add a key, then you go through the steps of substituting bytes, shifting rows, mixing columns, and adding a round key. You do that 9 times, and then the 10th time you skip one of those steps, and it just scrambles 128 bits of input into encrypted stuff. And these operations are chosen carefully to mathematically scramble the data and also to be really fast on a modern processor. So AES is designed to be optimized for modern computing hardware. And it, in fact, is very fast and very efficient and very secure, as far as anybody knows. Blowfish and Twofish came from the famous cryptographer named Bruce Schneier. He gives talks all over the place, and they come in various sizes, and it seems perfectly fine. Oh, it's not time wasting. No, this is probably the least time wasting. These operations, they're carefully designed to use the minimum amount of calculation required to make it secure. If you use one of these others, it will probably take a little bit more calculation, but still not that much. All secret key ciphers are very fast. Now, if you want to talk about consuming time, you want to talk about public key encryption, which we're going to get to, which is literally 1,000 times slower. Anyway, so RC5 and RC6 are from RSA Labs, and again, it comes in various sizes, and they're all fine. They're just not the one that won the seal of approval from the government. But now we get to public key encryption. The problem with all of those previous schemes, AES and Twofish and all that, is you still have a secret key, and you somehow have to get the secret key delivered to the person at the other end. Well, if you had some way to deliver the key, why didn't you just send your message that way? So you've kind of got a chicken and the egg problem here. I can send you a secret, but only after I'd find a way to send you a secret. So asymmetric encryption is what fixes this. And this was a top secret U.S. government technique that they kept secret and used for 20 years, but it was reinvented by mathematicians outside the government. And that's 1977. So each user has to make two keys, a private key you never tell anybody, and a public key that you share with everybody. And now anybody can encrypt stuff with your public key and deliver it to you, and you're the only one that can read it because you have your private key. That's the secret. So it is very slow, and but it is very good. The problem is you can only receive messages. If you want to send a message to somebody else, they have to prepare their own public and private key. So I think it's very much like this mail slot in your door. You can set up a system where people can put a message in, and you have the key so you can read the message, and it's reasonably secure as long as this lock is secure, but it doesn't mean you can send a message to somebody else. It just means you can receive a message. You need the person at the other end to make their own system to send them a message. And this is a problem. Ed Snowden wanted to send a bunch of military data to people to expose it. He was the guy that leaked out a bunch of military data. He finally had to flee, and he's now hiding in Russia from United States prosecution. And when he tried to send it to a journalist, he said, we have to send this with public key encryption, but he couldn't do it because the journalist wasn't able to create their own public-private key. No, it's not days or weeks. You use it in your browser all the time. It happens in seconds on modern computers, but it is much slower than AES. No, it's not. No, you'll see it. But if you, it can take a few seconds to generate the key, that's all, on a modern computer. Anyway, so you have to have a one-way function. So you have to have this system where the private key, you can calculate the public key from it, but people who can see the public key cannot find the private key. So you have to have this one-way function, a calculation that's easy to go one way, but hard to come back. And those are kind of mathematically debatable. So the actual security of public key encryption is not easy to calculate and not mathematically proven. But in practice, it works fine, and we're all using it all the time. Every time you use the internet, you're using public key encryption. So you need a one-way function. The original one was factoring a large number. This one has been famous for more than 2,000 years. If you multiply two numbers and you look at the product, it is very difficult to figure out what two numbers are multiplied to make that product. It turns out to be extremely difficult. So if you make the final number more than 100 digits long, it becomes essentially impossible to find the two numbers that were multiplied to create it. So the fundamental primes make two primes, and that's your private key. And the product of those two primes is the public key. That's what RSA did, the original algorithm. There's another one called discrete logarithm, and another one called elliptic curve cryptography, which turns out to be 20 times faster than this. This is very slow compared to AES, but elliptic curve is better, and that is the current most recommended procedure used by modern cryptography and by most modern systems. It's considered the best and most efficient system now. So, but here's a comparison of the strength. This took me a long time to understand. The asymmetric, which is the public key systems, have to be much longer. So, for example, triple DES is 112 bits symmetric key length, But if you wanted to use discrete logarithm or RSA, you would need a 2048-bit key. That's why it's so much slower. The key has to be much longer, 2000 bits instead of 112 bits, and that slows down the mathematics a lot. But elliptic curves is only 224 bits to match 112, so that makes it much faster. So elliptic curves are the most efficient public key system, but still a lot slower than a private key system. But you no longer have to deliver that secret key, and that makes it essential for the internet. Because if I want to read my Gmail, I just type gmail.com into a browser, and I want to send a secret to Google, like my password, but I don't have any way to deliver a key to them, so you use public key encryption to deliver an AES key, and after that you use AES. So that speeds up the final result. The only thing you typically send using public key encryption is a private key for one of these faster routines. That's the most efficient way to do it. All right, and then you've got the hashing algorithm. A purpose of a hashing algorithm is just to make a fingerprint to put on a file. So if I download something like an executable file, you can calculate a fingerprint. So by just combining up the bits to make an MD5 or SHA-1 or SHA-2 or SHA-3 hash, which is just a fixed random looking value, and then if it matches the value it's supposed to be, then you know that file is downloaded accurately. MD5 is the original common hash, but it's considered insecure. It was too short, and it's possible to alter a file and then add some more alteration to cancel out the first one, so you can trick MD5 into telling you it's the same file when it isn't. SHA-1 is much better, but Google managed a few years ago to actually find two files that are different with the same SHA-1 hash, so it's no longer considered completely trusted, and so we're all supposed to be using SHA-2. And there is one after that called SHA-3. A digital signature is more than a hash. A digital signature is a hash that is then signed with a private key, which we'll talk about later. So it proves not only that a file has not been altered, but it identifies the author. So it proves authenticity in addition to integrity. A hash alone proves only integrity, meaning that this file has not been altered from its original kind, for something like a download or a Microsoft update. But a digital signature further proves that you know exactly who sent it, and it has not been altered. So that's why it's called a digital signature, because you could sign something like a loan agreement with a digital signature, and now you have agreed to pay a certain amount of money every week or every month, or they will repossess your car, and they can hold you to that because it proves what you agreed to and that it was really you that agreed to it, like a signature. That's a very good question. All right, so hash functions, the whole point of a hash function is you should never be able to find two files with the same hash. So that if I look at the hash, I know this file is accurate, and that's the problem. MD5 and SHA-1 both have known collisions, so they're considered not perfect anymore, and SHA-2 is considered still very reliable. There are no known collisions in SHA-2, and we don't expect to find any because it's long enough that it would take millions of years to find one. So let's take a look at some cahoots, 3G. Good. Lots of good questions. $125. 3G. Good. 22. I'll wait a few more seconds. All right, guess that's it. All right, what's the strongest system on this list? Good, the one-time pad. Essentially perfect and unbreakable, but there's a serious key distribution problem. All right. All right, which process uses no key? All right, that's what hashes do. Hashes are just a fingerprint put on a file. There is no key involved. All right. If you encrypt bits one at a time, what are you doing? All right, and that's a stream cipher. I see a question. Your private key is associated with your Gmail account. It is, but in fact your browser makes a new key for every time you reopen the page, so it's only used for one session, and then you make a new one. Google has a private key that sits on their server, and you use the same one for years at a time, and they have to pay money for that one. Your little one is made temporarily by your browser. It's the same size, but it's used only per session. Good. So that's a stream cipher, encrypting one bit at a time. So which mode preserves patterns? Okay, that's electronic codebook mode, and that's a very good question, dice creation, and I'll show you right after these cahoots a good example of that. You're right on target. The kind of key that you create to be the client watching Gmail doesn't really prove your identity very well at all. Anyway, all right. So what's the weakest scheme on this list? Okay, that's DES, the weakest one there. One is too weak to be trusted. And what's the popular system for mobile devices? The elliptic curve system, because it's faster and it doesn't use as much battery power. All right. So I know who that is. And I know who that is. Okay. And hello will have to tell me who they are if they want their points. I see. Okay, good. Okay. All right, so I know who these people are. And let me answer a couple of questions that came up during the Kahoots. One of them, he's asking about how these signatures work, and I've got an example right here now. If you finish this class and get an A, you should get a CISSP certificate, and that's all that matters. But for any of my classes, including this one if you like, I have issued some badges students can get. So, because I've had requests for this from, I think, primarily perhaps for the students who are not official college students. So I made badges, and these badges are executable files. And when you run this exe, it will just show the name of your class and a logo and your name. And those are signed with digital signatures, authentic code signatures. If you right-click the exe and go to properties, it will show it's signed by InfoSec Decoded. And if you go to details, it will show you the signature is okay. That's what a digital signature is. And in order to do that, you have to buy a code signing certificate, and you have to prove to the certificate authority that you are a real legitimate company and not somebody writing malware. So you can't do this for free from your browser. You can't sign anything in a way that will really prove much of anything, because you have to have a public you have to have a real digital certificate with a certificate trust chain that goes up to a real trusted certificate authority. And I did that, and it took a long time, and it was really pretty difficult to do. It took maybe months to get this. But now I have it, so I can now sign code, and anybody that wants to sell software has to do this. The code you download for programs you buy, they're pretty much all expected to be signed. And if you try to run code that is not signed, you'll often have warning messages popping up saying, hey, this code might have been altered. I don't know who wrote this. This might be a virus. So any kind of commercial product goes through this process of paying for a certificate. So the cost is pretty high. The cost can be a few $100s a year. I found a really cheap provider, which is part of why it took me so long to get it. But I think I paid like $200 for 3 years, something like that. And normally it's like $200 per year. So it's not cheap at all. But you have to do it if you're going to distribute things. And I wanted to have it not only to make these digital badges, but also I'm planning to start signing all the code we use in my classes. Because really, you shouldn't be downloading code and running it without it being signed. So anyway, I wanted the ability to do this. And there's a project in one of my classes where you can make a certificate and sign things, but you won't pass this test because you can't get a certificate for free that will really pass this test. But you can go through the steps and understand how they work with the so-called self-signed certificate. And that is mathematically identical to this, but it won't pass this test right here without really leading to a known trusted provider. Anyway, so that's what digital signatures provide. And there was another person who made a username with some other system here. Think twice before using. So this is, I don't know about this. From last year in Wired, this looks a single site. Oh, they're talking about using Google and Facebook to sign on everywhere, which is what most people do. Like I just signed into Kahoot through Google. A lot of people do that. That's single sign-on, and it creates a single point of failure. Well, sure, if somebody gets in your Google account, then now they can get through everything. Yeah, you have to convince them. Yes, you can. For code signing, I think you have to be a company. I'm not aware of any individuals that have code signing certificates. You would have to discuss that with the company you're buying it from, and they have their own. The different companies have different rules. I had to get a letter written by a lawyer and notarized. That's how I finally convinced them I was for real. They would really like you to be a company, and they would like to be able to research you and find your website and call the company and make sure that you're really a company with a known reputation and such. Because if you sign malware with it, then everybody's reputation suffers. So they just want to be sure that you're not going to be distributing malware or sloppily losing the key and letting other people sign malware with it and such. Anyway, this is a single sign-on system. If you use Google or something, then that's a single point of failure. I painstakingly create a username instead of, either system is okay. I understand. I like using Google just for convenience, but you could argue either way. The most important thing, decryp, is make sure you don't use the same password in more than one site. You should use a password manager or something. That's the most important thing. Anyway, all right, those are good questions. And let's get back to here. So now we'll talk about attacks. The simplest attack is where you try every possible key. So this is what's wrong with, say, DES. There's 56 bits in the key, so there's only 2 to the 56 possible keys, so you just try every key until you can read the message. That turned out to be possible with a 56-bit key. 2 to the 56 is not a big enough number. So, but if the key is longer than 100 bits, this is no longer possible. All the computers in the world running for all the time in the world could not do 2 to the 100 calculations. That's an unthinkably huge number. So, for a symmetric key, anything over about 100 is going to stop brute force attacks. For an RSA key, it has to be much longer because the mathematics involved in public key encryption is more complicated. Anyway, then social engineering, of course, just trick a human into giving you the key. This is, of course, the standard way espionage has always worked. You don't really attack the technology. You attack the humans. You bribe them or trick them or seduce them or something. And that, of course, mathematics will not save you from that attack. Now, you can use a time-memory trade-off to do things like crack hash routines, where you have a pre-computed table that does some of the math. So by storing a big table in RAM, you do less cycles. And this was good for cracking Windows XP's password hashes. Modern systems are designed in a way that makes this less practical. Can we see our private key on our phone or computer? It's not easy to see. They don't make it easy. I think in your browser, I don't think there's any easy way to see it in your browser. I think there was a time when you could export it you could modify Firefox into saving your session keys, and you could export it into Wireshark, but that was only before Edward Snowden. With TLS 1.0, an older version of transaction layer security, you would actually use the same key every time you connected, and you could export that by modifying Firefox, and you could import it into Wireshark and decrypt the stuff. But they changed that with the modern versions of TLS, so it actually uses a different key for every session. And so I don't think there's an easy way to do it anymore. Of course, it's not normally done. But in principle, your browser does have the private key. It just doesn't make it easy for you to see because most people don't care. Anyway, so you can have a known plaintext attack. The only way to get your private key would be to put malware in your machine and hack your browser. And then, of course, they could view all the data from your computer before it gets encrypted, and they could also steal the private key. The private key is going to be in the RAM of your machine. So if somebody has malware on your machine, they could read it in principle off your machine. Anyway, so known plaintext attack is where if you know what the plaintext is that was encrypted, it might make it easier to deduce the key. And if you look at wireless encryption protocols, they're particularly vulnerable to this, because if you look at wireless traffic in, say, Wireshark, or any kind of network traffic, a whole bunch of it is just repeating the same question over and over. I am 192.168.1.100. Where is 192.168.1.1? ARP packets are what most of the traffic is, and they're all pretty much the same. So you can see a lot of packets, and you really know what most of the plaintext in them is, even if they're encrypted. So that's how WEP cracks worked. Then there's a chosen plaintext attack. If I can feed in plaintext and it will encrypt it and send it, which is again common on networks, then I might be able to find ways to carefully choose plaintext that will leak out information about the key. And that's part of how padding oracle attacks work, and beast and crime and other attacks. You feed it carefully chosen data, and when it's encrypted, you gain information about the key. So then the meet in the middle attack is why we use triple DES instead of double DES. Instead of trying to crack an encryption scheme all the way, you do half the steps to get in the middle. And then you crack the first half separately and the second half separately. So now instead of cracking a 128-bit key, you crack two 64-bit keys. So if you can somehow stop the process halfway and run it backwards, and that's called meet in the middle, and it greatly speeds up cracking calculations. So this is why we use triple DES. There are 3 steps, so that even if you break it in the middle, one side of it has 2 56-bit keys. So it still takes at least 112 bits of key to do a meet in the middle attack. And then, of course, there's known key. If I can somehow learn something about the key, then I don't have to try every possible key. For example, if the key is on dictionary words or based on a password that's all uppercase, then the key is not as difficult to find. All right. Differential cryptanalysis. You encrypt 2 plaintexts that are only slightly different. And then if you compare the ciphertext, you might deduce something about the key. If your encryption scheme does not have high dispersion, that means a small change doesn't spread out through all the ciphertext properly. There are side channel attacks, which are very dangerous. And that's what he was saying. How would somebody get your private key? Well, if they had malware on your machine and they could see your RAM, they could find the key. And maybe they could look at the radio emitted by the processor, or the power consumed by the power supply, or the time it took to calculate various encryptions. All these might leak out information about the key, and those are called side channels, where some other communications medium is being used to get extra information to help break the key. It turns out to be extremely difficult to avoid these side channels. And then there are, of course, implementation attacks, where the mathematics might be fine, but the actual way you implement it on the real hardware made a mistake of some kind, like leaving the plaintext in RAM, the side channel attacks, you do what you can. A famous side channel attack, do I know one? Oh, the most common one is Tempest. Tempest is the original one. Tempest was a U.S. military project to find out how much information you could get about computer operations by looking at the radio emitted. And they discovered that you could, if someone had the old CRT monitors, you could see what was on the screen by just picking up the radio, even if you were like yards away, looking through a window. So they decided what you needed to do was be in a closed metal room in a basement with metal all around you and no windows. That was a huge, and another one that you've probably seen in movies is you can send a laser and bounce it off a window and look at the reflection, and you can hear all the words spoken in that room because the glass vibrates. And if you shine that off the keyboard on a laptop, you can tell which characters are being pressed by looking at the vibrations of the laptop. So all those are side channels where when you type in something, it gets encrypted, and the data that goes out the network wire is perfectly encrypted, but the vibrations of the keyboard while you're typing are not random, and you can pick that up by looking through the window with a laser. So, that's the problem. You think you have a secret, but that's only if you play by the rules. There are other ways to learn your secret that you didn't think of, like I could just stick a camera in your room and watch you type. Now you can encrypt it all day long, and who cares? I can see what you're doing. Yeah, shoulder surfing. So that's the thing. No encryption saves you. Encryption only stops one kind of attack. I can always just bribe somebody into telling me the secret too, and then what good did your encryption do you? Yeah, differential power consumption from a chip, that totally works too. There's another one where if your chip makes mathematical errors doing the calculation, that has a non-random result on the output. So if I just make you encrypt it over and over and over again until a cosmic ray comes through and causes one bit to flip, if I wait until I have 100 broken encryptions, that's enough to break modern RSA. So there are many little real implementation issues. When you really build real hardware and do it, there are unexpected consequences which cause there to be attacks which do not really involve breaking the fundamental mathematics. They involve finding out the secret through some flaw in the way you've actually implemented it. And then, of course, if you do want to crack hash values, people were talking about how to crack hashes with things like John or Hashcat. So the way you crack a hash is you have just a big list of passwords, and you hash them all and try to find the one that matches your hash. So the question is, how long will it take to find a hash value? And if you want to just find a hash collision, 2 files, then it turns out to be a lot easier than you'd think. For example, if you have a room with 23 people and you get everybody's birthday, just name and month, there'd be 365 possible days in the year. So you might figure you'd have to have 180 people before 2 of them would have the same birthday, but you really only need to have 23 people before 2 of them will have the same birthday, because there are so many pairs. The first student could match the second student, or the first student could match the third, or the second student could match the third. So if you have 23 people, there are 23 times 22 over 2 pairs. And you'll typically find 2 students with the same birthday in a class with only 23 people. And so if you have MD5 collision that's 128 bits long, if you calculate 2 to the 64 hashes, 2 to the 64 files, it's very likely that 2 of them will have the same hash. So you only have to get up to half the length of the hash before you're going to find a collision. And that's why MD5 will never work. It's only 128 bits, and half of that is only 2 to the 64 bits, and that is an achievable number. 2 to the 64 calculations is something you can do these days. So that's why we use longer hash functions, like SHA-1 and SHA-2. So when you implement it, we've talked about this before, if you want to sign something and prove that you wrote it, like signing with a pen in court, what you do is you have a document here, something you want to sign, you calculate a hash like a SHA-1, then you encrypt that with your private key, and that's your signature. Your public key is known to everybody on a public key server, so anybody that wants to can verify. They can decrypt this and make sure the hash matches, so that proves that you signed it because you're the holder of the private key and you never share your private key with anybody else, and it proves that it hasn't been altered because the hash matches it. So that's what a signature proves. A signature proves you signed it and it has not been altered after you signed it. So you can sign something like a loan agreement. This gives you authentication and integrity and non-repudiation. You can't deny it later. But it does not provide confidentiality. There's nothing secret about this signature. This would be a public document, it could be a public document like a loan agreement, like a mortgage agreement for a house. Those are public documents, but the signature is just a mathematical way of signing it. This was defined in the Digital Millennium Copyright Act in 1999 under Bill Clinton to make it possible to do financial transactions over the internet, and it works just fine. So you verify it, like say, by reversing it. You take the signature, you decrypt it with the public key and get a hash. Then you take the document and calculate the hash. And if these match, that proves that it is a valid digital signature. All right. Now you can have a message authentication code. Yes, someone can pull up your mortgage. Yes, your mortgages are public records. And this is one of the common things that detectives do. One of the most common things detectives do is credit searches, where they will decide whether it's okay to loan you some money, or if you're like getting sued by somebody, they will first hire a detective to figure out how rich you are. So they will search public records. They can find out if you own land, if you own a car, if you own a house. They can find out what kind of job you have. All these are public records, and detectives will do that so they can decide whether it's worth suing you and how much money to ask for in a lawsuit. Yeah, those things are all public records. They're not usually too easy to find, though, so people usually pay private detectives that just learn how to find those records efficiently. Anyway, so you can have a message authentication code on a message, and this does the same thing for any kind of message you want using hashing and a shared secret key. And there's different modes like CBC-MAC and so on. These are used a lot by financial transactions. Yeah, LexisNexis has it. Yeah, there's lots of ways to get it. All right, so HMAC is a hashed authentication code using a shared secret and hashing algorithm like MD5 or SHA-1. This is just a way to put an extra tag on a message so that when it gets to the other end, they can verify that it has not been modified. And the public key infrastructure is what I was talking about before. This is why I can sign code and other people can't, because you have to have a known public key. And this is the public key infrastructure that does this. It's the HTTPS system where you have a public key signed with a digital signature which goes to a trusted certificate authority. Now you can bind it to a person or to a server in principle, and the nicest thing would be to have both ends using certificates, but that would get expensive. So you have certificate authorities, are these about 100 companies that have good reputations that are trusted by people who make browsers, and then you have registration authorities and certificate holders, clients that validate signatures, and repositories that hold their certificates, and revocation lists, which are lists of certificates that are known to no longer be trusted because somebody lost a private key or for some other reason. And there's a new system called Online Certificate Status Protocol that is a new version of certificate revocation lists. But anyway, these are all the things in the public key infrastructure system that make it possible for people like Google and me to sign something, and then your software in your computer can verify that that is really me. Would any of the certificate authorities report to other country governments? Well, some of them are infiltrated by governments, like China. The Chinese government can sign things, and your browser will accept it. And they have been caught forging other people, like Google and stuff. So that is a huge problem. You have to trust these certificate authorities, but they are just companies like insurance companies, and they do in fact have underhanded deals. They take bribes to sign things they shouldn't sign and to hand out their private key to people they shouldn't have handed out to. So like your bank and your government and everybody, they're not 100% trustworthy. But they are the system we're using. Sometimes they're even insecure and get hacked and let criminals steal their stuff. And when that happens, they go out of business. But if they cooperate with espionage, with like their local government and their local military, that is generally accepted. And even with large corporations, that's sort of accepted, but it's considered somewhat scandalous. So, I say you can trust them as much as you can trust a bank, which is, mostly they're okay, but there's a little bit of underhanded, sneaky stuff going on that we all kind of know about. That would probably be better if it wasn't there, but you can't do anything about it. So you have to protect your private key, so you have to back up the key in case your server crashes, but you can't let anybody else have it. So what you usually do is key escrow. You break the key into several chunks, and you store part of it at several different servers so that they don't have enough to break in, but if you lose it, you can retrieve the chunks and reconstruct it. That's a key escrow system. The United States government has several times tried to pass laws requiring you to give all the private keys to the government so they can read everything. And various systems like Microsoft operating system has the ability to back up keys in this way, to hand over a copy of the key to the government, but it's not turned on because those laws never passed. But that is something they keep trying to pass every couple of years, is the government would like to have everybody's secret keys, so you can't hide anything from the government. But that has not passed in America yet. It has absolutely passed in other countries. This got BlackBerry in trouble. When they tried to sell BlackBerry personal digital assistants to people in the United Arab Emirates, they said it is illegal for us to have stuff encrypted going back to Canada for BlackBerry, so they had to put a server in the United Arab Emirates where everything is encrypted only to that point, and then decrypted so the government can examine it before it goes on, because they won't let you have any encryption in the system that the government can't get into. But in America, we do have encryption that the government can't get into. Yeah, Microsoft by default stores the BitLocker private key in the cloud. That's true, but it doesn't hand it over to the government, not without a court order. The same thing's true of your Apple iCloud. Apple has the key and they can get into it, but they will not hand it to the government unless they get a court order, but then they will. So that's right, but you could choose not to back up the key in the cloud, and then your Microsoft BitLocker key would really not be available to the government at all. Nobody could hand it over. But if you were in the United Arab Emirates, that would be an illegal operation. Yeah, anyway. So SSL is the Netscape invention to encrypt data on the internet. There was nothing before it. And SSL is now no longer considered secure. It got out of date and it's replaced by transaction layer security. You can add your own encryption to anything before storing it on the cloud, yes. And then you could just hold the key. You totally can, and if you do, that's another layer of security. The problem is, if you lose your key, nobody can save you. And that's mostly what people do, just like their password. People keep losing their keys and their passwords, so most people are better off backing it up someplace because they're not really trying to hide secrets from the government. They're just trying to hide it from criminals. But you totally can encrypt something with your own key and take the responsibility of key management yourself. Yeah, a lot of people lose their Bitcoin keys. Yeah, if you don't back up your key, then you're going to lose your Bitcoin keys. And a lot of people lost their Bitcoin. I think something like 8 or 10% of all the Bitcoin in the world has been lost by losing those keys. That's the problem. You take on a responsibility if you don't let somebody else have a copy of your key. Anyway, so TLS is the new version, and so it's quite a chore to make an internet connection now. If you try to make a 23%, wow, that's worse than I thought. So if you try to connect to a server like Gmail, then here's what you do. First, you send a SYN/ACK, these are Wireshark packets, to open a TCP connection on port 443, and then you send a client hello message, which tells it, okay, I'm a web browser of this version on this operating system, so I can talk these 10 ciphers. Then the server sends you a server hello, and it says, okay, how about we use this one? And then you choose one. Then the server sends you a certificate. Then you you interrogate the certificate authority to say, is this certificate valid? And if it's validated, then you do a change cipher spec, and you agree on a cipher system, and now you start sending encrypted data. And you set up a public key system like ECC usually, elliptic curve, and the message you send with that is an AES key, and then from that point on you just encrypt everything with AES, having used public key encryption to deliver the secret key. It is quite a few exchanges required to set up a secure connection, but your browser does it in a couple of seconds, and everybody's doing it all the time now. Turned out to be extremely efficient and really quite secure. It is not easy to break into this system, although nothing is perfect. So then there's IPsec. This was an encryption scheme designed for IP version 6, and it was so valuable it was backported to IP version 4, and now it's considered the most secure way to make a virtual private network. It's very complicated. It has authentication headers, encapsulation security payload, these ISACamp and Internet Key Exchange, and I don't think it's worth understanding all the details, but you should know all these terms that go with it in the CISSP level. The authentication header gives you authentication and integrity, but no confidentiality, so I don't even know why this system exists. You should pretty much always be using the ESP version that provides confidentiality by encrypting the packets. And so what it does is it makes a security association that lets you send data one way. So for two-way communication, you have to make two separate security authentications, one to send and one to receive. And sometimes you even need 4 security associations if you're using some of these other features. And so then you have this thing called ISACamp that manages creating the security associations. And it has a security parameter index to identify the security authentic associations. There's a tunnel mode and a transport mode that encrypts data but not the headers. And there's an Internet Key Exchange protocol used as part of it. And anyway, it can go on for quite a while. Anyway, that's all IPsec. Now, Pretty Good Privacy is a public key encryption scheme invented by Phil Zimmerman in 1991, and I really feel for this guy because I was trying to do the same thing about a decade earlier, and I did not succeed. And boy, I'm lucky because he just opened a can of worms by doing this. He wrote public key encryption that you could use to send email, and he just published it to the world. And then he ran afoul of U.S. military law, saying that you aren't allowed to export high-quality cryptography outside the United States without an export license, and we wouldn't let it go to certain countries. So he spent years under threat of prosecution and everything else saying, you exposed a dangerous military secret to our enemies. And he was just, like I was, thrilled by the mathematics and said, this stuff is awesome. Everybody should use this. This is the greatest thing ever. So anyway, they eventually knocked it off with the Wassenaar Agreement and said, all right, everybody can use it. It's just mathematics. The thing about it is it didn't have certificate authorities. So you have to use a web of trust where users vouch for other users and you trust like the friend of a friend. So anyway, SMIME is a way to attach files to email, and you can encrypt it with a public key infrastructure system. See, we're getting a little late. I'm going to go to these cahoots, and I think that's probably all we'll do today because I think that's enough. Anyway, escrowed encryption is where a third organization holds a copy of the key pair. And as I said, this is something that would be a way to allow law enforcement to have access to the key. And it's not used in America, but I'm pretty sure it's being used in other countries. You could do it as some kind of backup system, but it also could be required by the law for government to have copies of the keys, but it's not that way in America. So the U.S. government in 1993 tried to make everybody use this Clipper chip so they would have the escrowed encryption standard, like I was saying. They tried to do it, but they abandoned it in 1996. And the last kind of encryption is steganography, which hides the fact that you're sending a message entirely. It makes a covert channel where you don't even know you've sent, your people don't even know a message has been sent. This is what terrorists use on the internet. They will have a deal that the secret you need is hidden in the 14th kitten on a page of images. You look in that image, and in that image there's a secret message. This is what the Russian spy Anna Chapman used in Washington. The movie numbers, I don't know anything about the movie numbers. Anyway, so this is where you hide something inside another file. You can take an image and you can change some of the colors and hide some other message inside there. That's called steganography. And another version of it puts watermarks in images, so every movie you see might be a little different than the other ones, and then they can tell which one was like being used to make copies. Anyway, all right, so let's do these cahoots, and then I think that's enough for today. We'll do the next bit another day. So we're here, 3H. So we did G already, and now we're going to do H. Yeah, printers use watermarks. Yeah, it's a fine example. Yeah. There are little yellow dots on your documents with your printer to identify which printer was used. I don't know how they got Reality Winner. It's a good question. That might have been it. I'll give it a few more seconds. Oh, all right. All right, so how long should an RSA key be? (2048). When they originally wrote it, they said use 512, but computers got faster and that's not safe anymore. The current recommendation is 2048 bits. All right. All right, what attack defeats 2DES? That's it. You meet in the middle, and then it's almost as weak as single DES. All right. What attack deduces the key from electric power consumption? All right, that's a side channel attack. Good. All right, what system ensures that public keys are authentic? Okay, that's public key infrastructure. All right, and what system uses AH and ESP? Okay, that's IPsec. All right. All right. Now to tell me who they are. I know who that is. All right, and I don't know who that is. All right, so I'm going to stop the recording.